Good afternoon, everyone. So Bertrand Tavernier from Thales, and I will present with Neel Gala from IITM this work, which is associated to, we named it SafeRV, and we will discuss about building blocks and also architecture exploration for safety critical RISC-V system. And that's the beauty of RISC-V, which is it has really enabled a concrete collaboration between Thales and Madras Indian Institute of Technology based on concrete objects, and we have shared and explored quite innovative architectures that we will present today. And all the outcome of this work is also in open source and open source hardware, and it's something which can be accessed and which can be shared among the safety critical system community. So this is, as I said, this work is the result of a collaboration and a partnership that we have signed between Thales and IITM more than 1 year ago. And there is quite a big team which has contributed to that. Maybe just a few words about Thales mission statement. I'm not here to sell anything, and especially a satellite or an aircraft, that's not the goal. But just to explain that if we look to Thales mission statement, safety and security are two words which are really emphasis. And if we look to the vertical on which Thales is working, so we are working typically in avionics, we are working in space, in transportation, and in defense, and here I will really focus on the safety and safety critical system. But if we look to all the vertical behind that, we are talking about high-grade niche market. We are not talking about mass market. I mean, I would like to sell as much satellite as automotive or even SIM card, but that's not the reality. And this is also a strong reason why we first start looking at RISC-V. Because if we look to the computing market for safe and secure system, since I would say the end of Moore's law or Dennard scaling's law, we are having an issue. We are having an issue because now we compensate the end of Dennard scaling by the introduction of hardware optimization. And hardware optimization is usually not necessarily adapted to our market. It's usually driven by mass market, and safety is rarely associated to mass markets, even if automotive is changing a little bit the deal. But if we look to our market, clearly, we are not a mass market. The second thing is most of the time, the off-the-shelf components are designed for performance and not necessarily determinism. And it's now more and more made of heterogeneous accelerator with no programming model. So if I caricature the situation from our point of view, we buy, I would say, off the shelf a piece of hardware, and half of the surface can be used for our specific application and needs. And if we look to the remaining half of the surface, we have to downgrade the performance. So we change the configuration, and at the end, we use half of the performance of half of the surface. So we use 25% of, I would say, the performance and the surface of the core. And more than that, we also, such off-the-shelf component also include complex BIOS and firmware on chip. And in safety and security markets, this introduces a lot of trouble because we have to introduce complex monitoring, and we have to clearly understand how the 100% of the system on chip or the codes or microcontroller behave. And most of the time, this makes hardware usage difficult, expensive, and suboptimal. The difficulty is not only to buy something and only use 25% of the capability of the object, but we have to really justify that the 75% that we do not use do not introduce any issue in terms of safety, in terms of security, in terms of interference. And we typically have discovered that even if a core is turned off, it impacts and it can generate interference in the system. So there are a lot of challenges associated to that. And this is typically the reason which makes us looking at RISC-V and seeing how we could define, I would say, new and disruptive and safe by design architecture, which would make our life easier. This slide, just to make, I've seen that several times today, to answer to the question, if safety related to security. So we have some parts which are common between safety and security, and it's the one associated to software assurance and in the design. So as an example, in safety and in security, you try to demonstrate some property with a good level of confidence. And this property are always like, the system will always behave like this, or the system will never behave like this. And this is done through the analysis of the intended function, and also through the demonstration of the absence of unintended or malicious function. And the way we demonstrate that required, so typically open source hardware and open source software have very good properties if we want to demonstrate the absence of unintended or malicious function. Part of determinism and partitioning, I would say, mechanism are shared between safety and security. In terms of software assurance, traceability and compliance, and analysis of derived requirements, which are all the requirements that we had to introduce during the design to make, I would say, the system real, do not also introduce unintended or malicious function. Where safety and security are completely different, it's when we talk about history of service. So history of service is something we need in safety. It's a good mean of confidence. Typically, the fact that a specific system has, I would say, hundreds and hundreds of hours of flight test is something really important. And history of service is really a mean to provide confidence in the safety world. In the security, usually, we want to update, and typically DevSecOps is becoming, and agility is becoming something really important in order to maintain the system under good security conditions. And for that, it's quite different. If we look to randomization, typically safety world hates randomization, where in security it's something completely really important. And the last part, which is really important, is the fact that safety and security can completely diverge in the way we address residual problem reports, open problem reports. So typically, when we look to these standards in safety, at the end, we need to analyze all the remaining problems, and we need to demonstrate that whatever happens in the environment, the probability that two remaining problems occurs at the same time is completely low probability. In security, that's completely different, because if two bugs exist, and if someone is trying to reach the second one from the first one, at one time the probability would be 1. He will succeed. So it completely changed the deal. And as a consequence for that, and it's something which is usually shared in safe and secured system, we really want to have strong separation of concern between safety and security, which means that at system level, we want to have a safe and secure system. But at design and low level, we want to have a strong separation of concern between these two worlds. Just few words about safety critical application. So first, we think safety as top-down needs, and of course, at one time, we have building block, and we want to use bottom-up pattern and make these two consistent. As a must-have, we need to have temporal and spatial partitioning. IO-MMU, IO-PMP are key for that. And what is also quite important is the fact that we need to guarantee that worst-case execution time is completely bounded. This means that we need to master latencies, jitter, and we need to have a high level of determinism, which can change the way we manage, for example, the cache. And maybe also we need to sometime introduce a very specific design pattern dedicated to integrity, availability, or resilience against, I would say, undesired event at system level, like ACU. Typically in space and in avionics, we need to fight against that. For that, sometimes we introduce some design patterns which are not really efficient when you look to security, because typically introducing resilience through redundancy can also introduce issue in availability of systems if you are in adversarial worlds. So maybe just to describe what we did, taking into account our needs and our very specific safety needs, and how we could use architecture exploration and RISC-V in order to have a robust system on chip.
Thanks, Bertrand. So moving on, with help from Thales and the guidance and their expertise in the domain of safety critical systems, we understood that there are multiple parts of the system that require specific optimizations and specific features, right? And these range from enhancing the core, adding ECC protections, adding in more performance counters, having a monitoring core which can monitor these performance counters, these events parallelly without affecting traffic. The network on chip was something that was important to them, and having more determinism within the network on chip. And specifically also the cache coherence, where they wanted to explore how we could add more determinism within the cache coherency. And the most important part was this entire project was supposed to be scalable, right? We don't want to build just a 4-core or an 8-core, but it should be scalable to going much more than that. So as the title says, we are now trying to build building blocks. So we identified there are different parts of these, and each of them needs to be enhanced separately. So as you can see, the first one was it's an InCore enhanced C-class cores. So the C-class core is one of Shakti's flagship core, which has been silicon proven a couple of years back and is now able to boot Linux. So it supports the RV64 GC SUN instruction set. It has a separate I cache and a D cache. Both of these are ECC protected. It has performance counters and all 29 counters, and you have the ability to extend more number of performance counters. I'll be discussing that in some time. There's also the hypervisor support that we started off when the version was 0.3, but there was a drastic change when it went to 0.4. So that's still work in progress. We'll probably restart our efforts in coming January on that. We are also adding a stripped down version of C-class. So if you all know, the C-class is one of the most configurable cores out there. You can actually strip down the entire 5-stage pipeline to just support INC. So that's going to act as a monitoring core, which can program the NOC, program different features, the filters, the event counters, and give you real-time feedback on what's happening within the NOC. The most important and the critical work that we've done as part of this project is the network on chip. So we've added more criticality awareness within the chip. So if you're injecting packets or if you're executing applications which are high critical, they get more determinism and they get a bounded time in which they'll complete, as compared to low critical ones which will probably get stalled and have a higher latency. For the cache coherency, we've added an the L2 is the shared cache. So the evolving versions will have more levels of caches as well. So today we can support actually MSI, MOSI, and MESI directory-based protocol. So I'll be discussing how we've achieved that. One of the most important issues that we started off with Thales was they wanted event counters, and tons of them, not just 1 or 2 of them. And one of the limitations at that point was that C-class uses the write-back stage as accessing CSRs, and it was a flat indexing mechanism, right? So it was a single cycle CSR access read-write mechanism that went on. And when we started adding all of these 29 performance counters, each counter is a 64-bit adder. So you would have a fan out of 29 plus indexing all of them, and then there would be event which will be incrementing those counters. So it really ended up in the critical path. So the best way that we thought to move forward was to daisy chain the CSRs. So what we did was we split the CSRs, all of the CSRs that are available for machine, into 7 daisy chains. You can actually add more to it, but for now 7 works for us. So 7 groups to keep a balance of CSRs. And on the right-hand side, as you can see, this is the grouping that we followed. And this is important because if you don't group them right, you could face penalties when you're doing context switching. So you want to switch off interrupts, or you want to do, you want to change your MTVEC. So all your trap handling mechanisms should be accessible very fast. So we've kept them as group 1. Group 2 are scratch CSRs and some of your read-only registers, or configuration CSRs, which you don't touch very frequently. Group 3 are the read-only ones. You have the MHART IDs, the vendor IDs that you're going to probably look up and configure at boot time, and not much at all. And group 4 and 4 and above are the ones where we add all performance counters. Right now, you can split them. You can have 4 counters within group 4, and have 5 counters in group 5, and you can split them. And you can also have characterization saying group 4 is going to tackle only these events, and group 5 is going to tackle only those, the rest of the events, right? So as you can see, the minimum latency is 1 cycle. So if you're doing context switching or if you're doing anything related to traps, you don't lose performance. But at the same time, if you're accessing some of these event counters or performance counters, it's going to take a long time to maximum of 7 cycles, right? So they're highly parameterized to include what is required. If you're not implementing supervisor or if you're not implementing FND, the related CSRs are omitted. So it's a completely parameterized design as well. The other aspect that was important to this project was tightly integrated memories. They wanted scratchpad memories along with the caches. So we typically thought of two approaches to do this. One was actually have the cache ways switch between being a cache or being a tightly integrated memory. So to lock certain ways of the cache, there's low overheads because you reuse the same hardware, you reuse a lot of these caches, only the replacement policy changes. So that was one of the benefits over there. But what happens is you can face performance penalties. So you're going from 4 ways to 3 ways to 2 ways or 1 way, and not so much of cache happening, cache performance being exploited over there. And coherency becomes difficult. So when you switch from a particular way from being a TIM to a cache or vice versa, if it's part of the coherence fabric, you need to make sure that you've got that right in the software programming model. And the alternative was to actually have separate ways dedicated to act as TIMs, but still reuse the same hardware in terms of the SRAMs and how you're going to choose a line from a word and all of that indexing mechanisms. So that's the approach we've taken. We've taken approach 2, where we say that we're going to have 16 kilobytes dedicated cache and 16 kilobytes or 8 kilobytes or 4 kilobytes, how much ever you want. It's completely parameterized as TIMs, so that you don't lose out performance of the cache and you have access to scratchpad memories as well. So the next thing was to add custom CSR. So obviously RISC-V allows you to do that. It has these standard and non-standard regions. So we started exploring the non-standard regions and adding some of these CSRs. One of the first ones was basically, since we've added so many counters, they also wanted a feature which said that if the counter overflows or if certain number of events has crossed, we would like an interrupt to be generated, right? So we've added an interrupt enable saying which events would you like an interrupt to be generated. And the idea was you up count. So whenever you want, let's say if I have 10 cache, D-cache load misses, you store -10 in the event counter and you start triggering it. And as soon as it reaches 0, you generate an interrupt. That interrupt is actually sitting in the MHPM interrupt pending. That's the separate CSR that we've declared. And the logical OR of this CSR is what gets set in the MIP register or the MIE register in the custom section, right? Then we have a couple of other things like DTVEC, DEnable. These are related to debug, which says that certain cores can choose to not participate in the debugging, whereas you have that ability to set at runtime. DTIM base and bound. So we discussed about the tightly integrated memories. The idea is you can change the base and bound addresses at runtime itself. You can have different cores have different base addresses within the memory map address space. And obviously, we wanted certain features like you can enable or disable cache, branch predictors, FPUs, all of that available at runtime. So we have a separate CSR which controls these as well. Cache coherency was one of the important projects here. So what we did was we started using a tool called Protogen, which is from a team from University of Edinburgh. So what Protogen does is it automatically generates directory-based cache coherence protocols. And till date, it used to generate Murphy code, which can then get SSP verified. As part of this project, what we've done is we've given them BlueSpec backend. So what you do is you define the cache coherence protocol as a DSL. And instead of generating Murphy code, it actually generates BSV code. So you actually get hardware for everything that you define as a DSL, right? So by default, you get MSI, MESI, and MOSI directory and cache controllers by default. And the idea was next to prove determinism on top of this. So we are now exploring ways to add something similar to what PMSI has done recently last year, and see if we can actually create a DSL implementation of the PMSI and provide more determinism on the cache coherence as well. Fault tolerance was the other aspect. So we've added ECC or protection on the GPRs, pipeline buffers, and the FIFOs. The caches and the TIMs are also ECC and SecDet protected. The CAMs and the TLBs are also single error detection, so single and double error detections. And the good part about TLB is you don't actually need to feedback the error. You can actually just generate a TLB mess and carry forward. Protection for functional units, we have added a triple module redundancy. And as part of this effort, we've also done a triple lockstep core, which is not covered in this project, but it's available on the branches of the C-class core. And some of the works that's in progress is on the NOC. So we wanted to see if we can have time transactions and add more EDC or ECC-based support on the fabric itself. Network on chip, this was to add shaping features on the NOC, differentiate between critical and non-critical traffic. So we started to add two critical levels, high and low. And the arbitration policy comes into picture, which says that if you're in a high critical mode, you make sure that high critical packets get more leverage in using the fabric or using the NOC as compared to low critical packets. And if you're in a low critical mode, you don't distinguish between them, and you just use a simple round robin policy, right? So we've implemented this in Garnet 2.0. All of this is open source; it's available. So if you look at the diagrams on top, the first one shows the regular latency graph, and the second one says that if you look at only the high critical packets, the tail latency reduces. So the max latency for high critical packets is much lower. Whereas the ones for the low latency, the low critical packets, the latency has increased, so you get a larger tail. The idea is to now also have features which can reduce the maximum latency of the low critical packets as well. That will happen in the next versions. On the hardware side for NOCs, we've looked at OpenSmart. We've looked at implementing them and support various message classes. We've added multi-split support to it. Critical aware arbitration, custom link. So we try to use tile link, but because of the heavy concurrency of Protogen itself for the cache coherence, we couldn't directly use tile link. So we've created a custom link, which will probably get more formalized in the next versions. And lots of performance counters and monitoring cores. We've added a separate VNet on top of this NOC to ensure that we can use that for debugging, interrupts, interrupt channeling as well in the future versions. And yeah. So most of this works is distributed. These are building blocks, so they exist in separate repositories today, but eventually they'll all get merged down into the SafeRV project, and all of this is open source. All of this is BSD, so feel free to try them out. Thanks. Yeah, if you have any questions, we have a couple of questions. Yeah. So one of the reasons that we did the grouping that way was that there was a requirement saying trap handling and masking of the traps, all of that needs to be as fast as possible. But we don't really have real-world applications trying to exhaustively verify that. So